Khan, and this is my Physics 2 lab report for Lab 3 on the magnetic field of a bar magnet. So the goal for this lab is to compare the measured distance dependence of the magnetic field due to a small bar magnet to the distance dependence that's predicted by the Biot-Savart law. So we're basically comparing a real-life measured value to a predicted value that's a more ideal value. And for this experiment, the fundamental physics principles that we will be applying are, as I mentioned, the Biot-Savart law, and the formula for that is given at the top over here on the left. And distance dependence, we'll be using these two equations below Biot-Savart law to find distance dependence, as well as magnetic field of a dipole, which is the most bottom equation here. And here's a quick summary of the most important results from my lab, and throughout this presentation you'll be able to see how I got each of these results. So some observations from my experiment. I observed that when the magnetometer was far away from the magnet, it measured a near zero magnetic field in the x direction. However, as the magnetometer moved closer to the magnet, the x component of the magnetic field increased. And here is my on-field magnetic data. This is just a summary of the most important values that were calculated from my experimental results. You can pause here if you want to just take a look at it. Here's the full Excel file. If you want to see that, you can also pause if you want to. And here is the graph that was obtained from my on-field data. So from this graph, we got that the distance dependence, which is the slope of the graph, is negative 2.5059. We also got the magnetic field at 45 degrees, which is this value given here. And then from that, we can then calculate K, which is e to the power of our intercept value from the graph. And then we can plug our values into the dipole equation to solve for mu, and then we get our magnetic dipole moment to be 3.5. Here is the off-axis magnetic field data. Once again, you can pause if you need to. And then finally, we'll move on to the coding part of this lab. So I'll just talk about the most important parts of my code. So firstly, we used our mu mag value of 3.5 in line 19. That we just talked about how we calculated that. And so we plugged that value into the dipole equation. And then we found here's all the coding to find all the arrows in our final output, which you'll soon see. And then we also use the distance perpendicular value that we got in our off-field experiment results, and we plugged that in as well to get the what was the magnetic field, at 45 degrees. And here is the output of my code, which you can see on the screenshot on the right. And when we compared the output results to my experimental results, I mentioned that my experimental results had a magnetic field at 45 degrees to be this value, and then we see the value of the magnetic field at 45 degrees in my code output. And when we compare the two magnitudes, the magnitude of my experiment was 3.88 e minus 5 Tesla, whereas the coding magnitude was 2.63 e minus 5 Tesla. And so they're roughly similar to one another, I'd say. And now answering some final conclusion questions. So if we hadn't oriented our experiment to compensate for magnetic north, then the Earth's magnetic field would have interfered with our results, and that would make our experiment results much less accurate. If we stuck two identical magnets together and ran the experiment, then I'd expect that the magnitude of the magnetic field would increase, however, the direction would stay the same. And that's it for my Lab 3 report.